Thank you for the introduction. I noticed that you didn't pronounce my name, my family name, so okay. So it's really a great pleasure to be here. I wish to thank the organizer. And it's my first time I go down to the Calanque and have a swim, so I'm really enthusiastic. Today I will talk about Middlegame. So there have been several talks on that subject already. So I remind you that Middlegame is just about crowd motion of rational agents, meaning that each guy in the crowd is optimizing some criterion and interacting with the other players, the other people in the problem, and we see it at a game. So it's a kind of Nash equilibrium in this crowd. So because it's a Nash equilibrium, we can ask questions which are relatively classical in game theory, and the one I'm going to address today is the notion of efficiency. Meaning that, so in Middlegame games, people do, in principle, self-organize, and so in this sense, they are not necessarily, they do not do as well as would do a global planner. And the question is, how much, what is the difference between what they are doing and what a global planner would do in the same configuration? Okay, so that's classical topic in game theory, known under the very poetic title of Price of Anarchy. But okay, so here we call it inefficiency. I don't claim to do Price of Anarchy here. Okay, so let me start with a brief introduction, since the subject has already been discussed a lot on Middlegame, and then we move on the question of efficiency, and then we will complete the talk hopefully with a discussion on the convergence of Nash equilibria as the number of players tends to infinity. So we will start with a finite number of players and let the number of players go to infinity and see what's going to happen in terms, and in fact we will see that in this limit efficiency plays a role. So. Okay, so I can more or less keep that. You all know that Middlegame games are game theory in the framework of non-atomic games and in optimal control. So the payoff of each player is given by an optimal control problem, and people interact in a non-atomic way, meaning that each guy in the crowd is atomless, okay? He's very small. And this is a topic which comes from, in fact, originally from the economic literature, not from the crowd literature, but where under the name of heterogeneous agent models. So the first ones going, first works in this direction go back to Ayagari, which must be 84 and not 94. And then a few topics there. And it has been rediscovered by the math community and the engineering control community by Lasry Lyons and Keynes, Wang and Malamé, and you have seen two of them here in the previous days. So it's about Middlegame equilibrium, meaning that you try to understand what is a Nash equilibrium in a continuous time game. So the idea is that each agent in this crowd forecasts the motion of all the crowd and acts optimally in solving an optimal control problem. And when all the agents play optimally, their probability density, their position evolve in time according to a probability m tilde, okay? And there is an equilibrium, a Nash equilibrium, when the forecast is correct, okay? So this is what Filippo, for instance, explained. So here we are going, at least in the first part of the talk, discuss about problems in finite horizon. So capital T will be the finite horizon. I'll always be in a finite dimensional setting, in typically RD, or in very often with periodic boundary condition in the torus, D-dimensional torus. The initial population at initial time is called M0. So M0 is probability density on RD. And there will be cost functions, the running cost, which depends on the position of a small player, the control he plays, and the distribution of the other players. Okay, and there is a running cost and the terminal cost, which takes more or less the same form, depending on the position of the small player and the position of the crowd. Okay, and U will be the value function in general, and I call du the space derivative. So how does the Milligram problem work? So you assume that you have a small agent which starts at time t0 from a position x0, and he assumes that the population density is fixed, okay? And he solves the, let's say, to fix the idea, a stochastic control problem of this form where he controls directly his drift. So alpha t is the control, okay? This is the Brownian motion. And the problem he has to solve in this story when he forecasts that the players are going to move according to a distribution which is called here M of S. So M of S is at each time S probability density on the state space. Okay, his running cost is of this form, and his terminal cost is of this form. So this is his value function, and it's known, as Filippo explained, that once you know the value function, you know it satisfies the PDE, and even more importantly, you know how, once you have the value function, you know how to compute the optimal control, the optimal feedback of the players, which is alpha star, which is just the derivative with respect to the gradient variable. So P is the gradient variable of the Hamiltonian. Okay, so you can solve it completely once you know the value function. And now, if each of the player forecast has the same forecast on the evolution of the population, they are going to play alpha star, and therefore, by a mean field limit argument, the population density is going to evolve according to this equation where there is a tilde which is missing here. So it's the Laplacian comes from the Brownian motion of all the players which are supposed to be independent here, and the drift, which is just alpha star, the optimal drift. Okay, so you got that. So this leads to a system which is called the Milligram system, which takes this form here. Okay, so U being the value function of a small player, M the evolution of the population density, and let's strongly point out that the first equation is backward, so in the sense that it really means that you forecast something, and the evolution of the population density is forward, okay, evolving in time. So this is what we call the Milligram equilibrium. So what is known about that? I mean, there are plenty of results now. The literature is a little bit quite huge, so I try to put in a single slide some basic result on the subject. So existence of a solution is known, and I quoted Las Réunions, but of course Wang and Keynes and Malamé also did a significant contribution on that topic. Uniqueness does not hold. So in general, this is a game, this is an equilibrium problem, so you don't expect uniqueness to hold there. So so in general there are several equilibria, okay, but you can show we probably won't use it, but you can show nevertheless that if the coupling is small, so if H depends not too much on M, typically, or if you are in short time horizon, which boils down to the same thing, then you have uniqueness of the solution. Okay, and you also have a uniqueness of the solution when the Hamiltonian is separated form. So what I will call separated form means that H depends on the difference between a local contribution, depending on X and the dual variable P, and the interaction term, in which you see that M is here. So if it's on this form and F moreover satisfies the monotonicity condition as well as the terminal condition, then you have also uniqueness. Okay, so I won't use this monotonicity condition. However, I strongly use the fact that from time to time I need the problem to be in separated form. So, in what extent does it represent really a game with finitely many players, as the number of players tend to infinity? So this is correct in one direction. So from midfield games, once you have a midfield game equilibrium, it's relatively easy to build out of the midfield game equilibrium strategies which are almost optimal in an n-player game when the number of players is large, and this is one of the fundamental contributions of Keynes and Malamy. And I'm sorry, Laurent. Okay, there is a mistake in the name here. The other direction is much more involved, and so when you start with Nash Equilibria of n-player game, I will discuss that in the second part of my talk. It's much more delicate to show that the n-player game converges to a midfield game system. And as we will see in the moment, it's not always true, and we have to be a little bit careful in the modelization. So this has been proved for linear quadratic games and for open loop Nash Equilibria, so meaning that players only observe themselves in a relatively easy way, and then to go to closed loop Nash Equilibria, so to go to a configuration in which players do observe each other completely, okay, to a midfield game in which players do not need to observe the other completely. It's much more subtle, and this is what we did with François Delarue, Jean-Michel Essery, and Pierre Williams, involving an equation called the master equation, and Dan Lacker, that in a result that I'm going to quote at the end of the talk, has revisited this to prove that in some cases there is closed loop, there is a convergence of the closed loop Nash Equilibria. So here what I will discuss is mostly the efficiency of midfield game equilibria, so comparing the situation in which you have an equilibrium with a configuration situation where you have a global planner which tells each guy what to do, okay, and we will try to compare more or less the resulting global cost or the resulting global outcome, okay, and to understand in which case you have efficiency, meaning that the outcome is more or less the same. So we will see that of course it never happens, and we will try to quantify the inefficiency, meaning that we'll try to find a quantity which more or less weights how much inefficient is a midfield game equilibria. And then we will see that this question surprisingly pops up also when you look at midfield limit of closed loop Nash Equilibria. And we'll see that there is an example in an ergodic cost, so slightly different from what I'm going to present here, where because you have inefficiency, you don't, the Nash Equilibria do not necessarily converge to the midfield game problem. Okay, so what is efficiency? So this is a huge question, and I don't claim to answer that question because there is 1,000 papers in the game literature about this. But basically, okay, so as I said, we want to understand in what extent does a global planner do better than than Nash Equilibrium, okay? And to quantify how better it does, okay? So this goes back to Debye, and there is a huge literature on the price of anarchy that I will skip here. And this has been very little considered so far in the community of differential games, and even less in the community of midfield games. Also, probably for midfield games it's easier, and we'll see that there is a relatively easy answer. Also, I'm not sure it says a lot, but there is an easy answer for midfield game. And there are ideas in this paper also where in linear quadratic games there is an explicit computation, okay, or infinite Markov chains also. But somehow the results do not match completely, so I don't know how to compare them. So let's start with the setting. So let's first discuss about what is the best cost for a global planner. So to understand that, we start with the n-player game, and we're going to let the number of players go to infinity to see what's going on at the limit. So we assume that we have plenty of agents which control. So we have plenty of agents with alpha I, the control of agent I, xi, the position of agent I, and we look at the global cost. We look at the cost of player I, which is called gi, which is just exactly the same cost as before, except that I'm replacing, since we are in an n-player framework, the density of the players by the empirical density. Okay, so the empirical density which is here. And the cost for the global planner is the sum of the costs, or the average if you prefer to normalize, okay? And so it's a natural question to ask, what is the best cost a global planner can achieve in this model, in which he says to the player what control to choose, okay? And it's almost, it's very easy to see that as the number of players go to infinity, the optimal cost goes to a quantity that throughout the talks I'm going to denote by C star, which is just the control of the Mac-Inverse equation associated to the problem. So be careful here. I'm assuming that the control of the Brownian motion associated with the control problem of the players are independent, and that's important. The situation would be completely different if they were not independent. But because they are independent, there is a mean field limit which is deterministic, so which is here, okay? And so, as a limit, the optimal cost of the global planner, as the number of players goes to infinity, converges to C star, which is just the cost that you recognize, integrated against M, okay, in this way. And the measure M, which is a time-dependent measure, which evolves in time according to the Fokker-Planck equation. Okay, so that's the cost for the global planner is this one. Okay, and we have already seen what is the cost for the what is the Milligram equilibrium. So this is this quantity, and if you collect, so if you take a Milligram equilibrium U bar M bar, you have a social cost associated with this equilibrium, which consists in integrating the cost of each guy according to the measure M bar. So you have exactly the same quantity, okay, which is here. Okay, notice that alpha star is optimal cost. Okay, so you have two costs that we are going to compare: the one which is infimum, okay, of all these guys, and the one which is given by the same quantity, but for a Milligram equilibrium. Okay, and the question is, when is it equal? So, Milligram equilibrium U bar M bar is efficient if the cost associated with the Milligram equilibrium is equal to C star, and we will say that it's globally efficient if it's efficient for any initial condition. Okay, so it's easy, of course, it's easier to characterize global efficiency than efficiency for which you fix just a path. Okay, so my question is, how do we know that if Milligram equilibrium is efficient, and in which configuration do we know that it's globally efficient? If not, how to quantify that? So let's start with the characterization of efficiency. So to do that, I will need, okay, so I didn't say much about assumption. So we will see in a moment that we have always assumed that L or H for the are smooth with respect to the measure M, where as a function on the probability measure. So M is a probability measure on RD, or here it will be most of the time the torus. I'm going to assume that everything is periodic, so it will be on the torus. And I'm going to assume that L is sufficiently smooth function of the torus. So let me explain what is sufficiently smooth, but this was already explained yesterday by Jean-François. So we work on the torus, okay, so with on the Wasserstein space, endowed with, for instance, the D1 distance, but it plays no role. And we say that the function U, which is defined on this space, okay, which its probability measure is C1, if you can find a flat derivative in this sense, so that the integration by part formula holds, okay, like that. So as Jean-François explained this, let me go fast about that. And he said also that one important object is one important object is intrinsic derivative, which is, for a reason that I'm going to explain in a moment, the derivative with respect to the extra space variable of the flat derivative. So the reason why this derivative is important is that it quantifies, in fact, the Lipschitz regularity of the function U. Okay, so the Lipschitz regularity of U is not quantified in terms of the flat derivative, but in terms of the intrinsic derivative, for instance. Okay. Okay, so now let's move. So this is the assumption on the problem. So there are plenty of assumptions, so we will skip that. But basically, they say that everything is smooth, and L, the Lagrangian, and H, the Hamiltonian of the problem, have a quadratic growth, and they are related through a Legendre transform. Okay, so the first result is to okay. So the first thing is that we need to characterize a little bit what is the social the problem for the global planner. Okay, so the social cost. So that I recall here. Okay, so how do we characterize that? Well, this is related to what Filippo has been explaining. You have an you've got a calculus of variation problem in the space of measure, okay, of these forms, and the optimality conditions are known, and they are relatively easy. They say that if so, you try to minimize this. Okay, so if you have a minimum of the problem, then you can find a potential function which is here called u hat, which solves a system which is a Hamilton-Jacobi equation with the right-hand side, which is given by the flat derivative of L respect to n. So here is, and you see that here so we were optimizing over alpha, okay, and here we'll see that the alpha is given by this quantity, okay, so it's again minus dph, okay, and you have terminal cost like that, and you see that alpha is minus, in fact there is a minus which is missing here, dph, okay, so it characterizes the Equilibria, so the minima. Okay, so if you want to minimize this quantity, and you find at minima at the minimum point quantities m hat, w hat, which is in fact should be alpha hat. Okay, so which are the minimum, and u bar, which solve something which looks very much like a Milligram system. So it makes sense then to expect to be able to compare the Milligram system with this, because they solve almost the same equation. But this guy is not a Milligram system, okay, in general, for reasons that I don't have time to explain. Okay, so our first result is to say what happens when Milligram is efficient. So remember, Milligram is efficient if the cost associated to the Milligram is exactly the same as the minimal cost. Okay, and surprisingly, there is a formula. So in the framework in which I'm working, it's, I mean, I didn't expect to find a simple, relatively simple formula, but here it is. The formula says that if you have a Nash Equilibria, so Milligram Equilibria, which is efficient, then you must have that these two quantities are zero. So this quantity is a quantity which depends on time, where you look at the derivative with respect to the measure of L. So this is the guy which was appearing here, okay? So this guy must be zero, basically, and this guy must be zero. This is what says the result, okay? So this thing must be zero, so it's so you integrate the Lagrangian against the space variable, okay? And this must be zero for any x and for any t. So you see it's a very strong condition. And the same holds here. This must be zero for any x. Of course, it doesn't depend on t. Okay. So it tells you that basically in this setting, you find again the Milligram system because you have exactly the same kind of problem. Okay. Okay. So the proof is not completely fascinating, so let me skip it. And it's just plain computation. Okay, so I skip the proof because it's not very difficult. This is the reason why I call that a proposition. But the result is surprisingly clean. I mean, so let me skip the proof and let me give you the opposite direction. So to do the opposite direction, you want to know if it's true that a system is globally efficient and to characterize that. Okay. So to be globally efficient, of course, you need to satisfy the condition I wrote before. Which was true along a specific Milligram equilibrium. So I want to be true for any initial position and any Milligram equilibrium. So somehow you expect that this holds true, okay? But in order to come back, the fact that the system is globally efficient implies that this must be true. Okay, so this is more or less what is condition I had before. This is not surprising. What is more difficult is to prove that if you have this kind of system, the system is globally efficient. And this comes from the assumption that you have a separate form. And we need that to be able to conclude. Okay? Okay, so what it says is that you have complete characterization of efficiency in this framework. Let me give you examples, because of course these formula are really strange and I still don't know what they mean. I mean, so except in particular cases, I don't completely understand what they mean. So there is another way to formulate the problem, is to say, okay, my function f satisfies the condition which is here, if and only if it's the sum of another function plus its derivative. Okay, I know that doesn't help much, but okay, this is the best characterization I found. So in particular, in general, unless f, so f is a function depending only on m, okay, and plus its derivative. So unless f is affine with respect to m, this quantity is not constant in m. So this gives you a lot of examples of problems in which you have efficiency, okay? But there are only examples, and let's now look at what happened when you take typical problems that we encounter in practice, and as we will see, it doesn't work. Okay, so typically.
F is a running cost.
Sorry, F is a running cost. Yes. So I'm working in this framework where you have a separate form. You have the Hamiltonian typically. So of course there is it's a p here. Okay, so typically think of p square minus the coupling term, okay? And so here I'm interested in what's going on for the coupling term, and here is an example of coupling terms for which you have efficiency. Sorry?
If you go back in this formula,
there is a p, yes, absolutely, yeah. There are some typo in the text, and it's done on purpose for pedagogical reason to see if you follow. Okay, so this is a class of example for which you have efficiency. Don't ask me if it works. I mean, if it's interesting, I've got no clue. But here we are more typical examples. So I'm assuming that G is 0 and so on. Okay, so G is assumed here to be 0. H is a separate form, so I'm only interested in what's going on for F. Okay, and so let's assume first that F does not depend on X. Okay, so general fact F is a coupling saying, okay, that's a price I pay if I'm at position X and if the measure is M, okay? And so here I'm assuming that this function depends only on M, okay? So that does not depend on me. Then, okay, then in this case, the system is globally efficient if and only if, well, if and only if F is constant. So there are only constant, which means that basically it's never efficient for interesting problem. And the reason is just simple computations, nothing. In the same way, if you assume that F derives from a potential, so this is typically potential Middlegame that Filippo discussed, okay, meaning that you can find F as a derivative with respect to the measure of a capital function capital phi. Okay, then again, you can prove that you have global efficiency if and only if F is 0. So it's even more drastic. Okay. And to finish, a simple example of this form, linear case, okay, where f is some kind of convolution of the measure m with respect to a kernel phi, then again you can prove that this guy is globally efficient if and only if f does not depend on m. So basically, in most interesting cases, it's never efficient, which is not surprising. I mean, I didn't expect it to be efficient. Okay, so can we quantify this efficiency? Yes, so I'm going to show you formula. The only interest of this formula is that they still involve the same kind of quantity that was involved for efficiency, okay? Otherwise, the fact that they are optimal and so on, I'm sure they are not, but okay. At least they show that the quantity we found for efficiency plays a role and in a more or less quantified way. So take U bar M bar a Milligram equilibrium. Okay, so the social cost is always below the cost associated to this Milligram equilibrium, and in fact it's a positive quantity. So you see here that there are plenty of square and power 4, so this quantity is positive. Okay, so there is an epsilon which is floating around, which is related to the fact that you insist that you have a terminal cost which messes up the problem. But if G is 0, for instance, you can take epsilon equal 1 here and 0 here. So you really have the clean form minimum. Okay. So it's the integral of the derivative respect of L respect to M against M bar. Okay. So here like that. So what it says is that, I remind you that efficiency was meaning that this guy must be 0, okay? And if it's not 0, then it minorize the difference here. So, and you can have a bound from above in the same way under additional assumption, which involves the same kind of quantity. So I'm assuming now that F is separate form, and you have the same kind of stuff. Okay, so and you need some structure condition, which is not surprising here, because if you don't have structure condition, it's extremely difficult to compare something which is given by an equilibrium, okay, and something which is a minimum of the quantity, because an equilibrium is just a fixed point condition, which might be very far from the minimum, okay, and to overcome this difficulty of comparing two things which in principle should not talk together, we need some global assumption, which is here, the fact that these quantities are convex. Okay. Okay, so I'm mostly over with efficiency, and now I want to show you an example where efficiency is going to play a role in a quite subtle way when you want to let the number of players go to infinity in a finite game system. Okay, so let me start with the result due to Dan Lacker, which has puzzled me a lot, and I'm going to explain you why. And then we will move to an adaptation to the same result, but when the horizon tends to infinity. So we look at the mean field limit in a game. So we have n players, capital N is going to tend to infinity, and we have capital N small players, small in the sense that will appear in a moment. So they are going to play path-dependent strategies, meaning that they are going to observe the other player and play according to the position of the other player in the past. Okay, so meaning they are going to observe the trajectory of the other players. Okay, and they are going to give a control. RD here is a control space of the other. Okay, and so given a family of strategies alpha 1, alpha n for the players, you can solve the stochastic differential equation, which is here, okay, assuming that the BI are ID Brownian motions. Okay, so this equation has a solution given an initial condition. And the goal of the players, for each player, is to minimize its cost, okay, which is, as usual, the only difference is that, and this is how we quantify the fact that the players are small, they interact only through their empirical measure. So there is a small subtlety here which is that I look at the empirical measure of all players, but player I if I look at the cost I. Okay, so this is the reason why there is but okay. And we say that we have a Nash equilibrium in the n-player game if player I deviates and plays alpha I instead of alpha bar I, then the cost increase. Okay. And the main result by Dan Lacker, which is really surprising, is the fact that in this framework, okay, the strategy converges to a Nash equilibrium. Okay, what is proved really is that if you look at a Nash equilibrium payoff, okay, for the n-player game, you look at the empirical measure associated with this payoff. Okay, this guy converges to measure which is a kind of mean-field-game equilibrium. So it's a weak mean-field-game equilibrium. I don't have time to enter into the detail, but basically it's a mean-field-game equilibrium. Okay, so under very little assumption, you can prove that as the number of players converge, you have a mean-field-game equilibrium. It's surprising for two reasons. So there is, in differential game, a result which is called the Folk theorem, which says that, so when you have a finite number of players, they observe each other, okay, and an equilibrium in this setup is a quantity which is such that if one player deviates, he gets punished, okay, by all the other players, okay, and this punishment gives you a worse cost. Okay, I said it badly. Let me go back. The Folk theorem says that observing each other is very important in game theory because you can observe deviation of the other player and then therefore punish this deviation. So it's increased the number of Nash equilibria. Okay. So what Dan says is that when you let the number of players go to infinity, this is no longer the case because in infinite game equilibrium, what a single player does has no influence at all because it's very small, okay, and it doesn't affect the deviation in the measure, okay. So what is happening here is the fact that there is a very strong assumption, in fact, in this story, or an assumption in this story, which is that the dynamics. It could be more complicated dynamics, but what is really important is that there is a Brownian motion here, non-degenerate, and which means that when you observe a trajectory of a guy, you cannot know what it has been doing because of the Brownian motion. Okay? So that's Dan's result. Now let me move to what we did with, and I completely forgot to mention that all what I'm presenting here is a joint work with Catherine Reiner. So this last part is a forthcoming, it's an ongoing project. So now we are going to look at the same problem, except that we are going to let the horizon go to infinity. Okay? So exactly the same problem. The strategies are defined in the same way. We have n-player game. Each guy has his strategy. And we look at instead of looking at the finite horizon cost, we look at the ergodic cost, which consists in letting t go to infinity after dividing by t. Okay, so this is the classical ergodic cost, and we assume that we are in the torus in order to have a little bit of compactness. Okay. But this is the same problem, and you define a Nash equilibrium more or less in the same way. So let's keep the notation. We only work up to the level of epsilon Nash equilibrium, but that's all. Okay. And what is going on in this setup? So the only difference with Lacker's framework is that now the cost is ergodic, okay? And now what we proved is that, in fact, there is a, so first thing, there is a triviality. So let me point out that I'm assuming that F depends only on the empirical measure and not the position of the player. This is made to simplify, but also I'm not sure that the result remains if we put some x here. So what we proved with Catherine is first, okay, so the characterization of Nash equilibrium. So it turns out that in this setting, it's almost obvious to compute the mean field game Nash equilibrium because you first solve the problem without taking care of the coupling, F, which if you see the equation, once F of mu is given, it's just a constant. So you can solve the problem without this constant. And this only affects the ergodic constant, which is here, okay? So you solve this problem, and then you plug it in you find, so this gives you an optimal way to play without taking care of the F, okay? And then you can come back to find an invariant measure associated with this, with the drift, which is here, okay? And this gives you a mean-field game equilibrium with cost, which is more or less this one. Okay. So just to tell you that the mean-field game problem here is a triviality and there is a unique mean-field game. So typically a case in which you would say, okay, there is a unique mean-field game equilibrium, everyone should go there, okay? And it turns out that's not the case. So we can find a Nash equilibrium payoff, so symmetric in the sense that all the players get in the n-player game, they get this payoff, okay, which converge to the minimum respect to alpha mu of this thing. Okay, so this is the minimum, the social cost, in fact, in the ergodic problem. Okay, so, and, okay, so you can prove, okay, again, if, okay, I forgot to say something, if f is not constant, you can find a family of Nash equilibria which converge to the social cost, not to the Milligram equilibrium, to the social cost, okay? And as we saw in the first part in the efficiency, okay, in fact, the social cost is strictly less than the cost associated with the Milligram equilibrium, which is just this quantity here. Okay, so there is a unique Milligram equilibrium, okay, and you converge to something which is not that one, so, because of efficiency, because I'm assuming that f is not constant with respect to the measure, okay, so we know that in this setting you don't have efficiency, okay, so this quantity is strictly below this one. Okay. And the reason why there is a, okay, and I'm stopping there, the difference with Lacker's framework and this framework is that when you observe in finite horizon trajectory of a system which is perturbed by Brownian motion, in finite horizon you cannot deduce anything about the drift. This is not the case in infinite horizon, where you can, because of ergodicity, you can observe the drift and therefore punish the guy who does not play the drift which is planned by the player. And this is the reason which this explains the theorem which is here. Okay. Okay. So I'm over. So let me skip the proof. So to summarize, what we have seen is that we have characterized the efficiency for the min-field game and quantified it a little bit. Okay, and we have proved, we have explained a little bit how to apply this kind of ID to the min-field limit. So there are several open questions here. For one thing, the general question is it in any case useful? I have got no clue, okay, but I didn't write it down because. So there are technical questions which is that the upper bound, you remember, they are in the quantifying the efficiency, we discussed about the lower bound and the upper bound, and the upper bound relies on some strong structure condition, convexity, and I don't know how much we can relax that, okay? Here all the regularity properties I'm doing strongly relies on the fact that we have bounds on regularity bounds on the system, so I completely hidden the proof, but everything relies on the fact that we have a very strong smoothness, and I wouldn't know how to do that without this smoothness. For instance, if you remove the Laplacian, which are completely natural models also, okay, so if you don't have noise, how do we do that? I don't know, okay, so it would be a nice question. And also there are min-field games in which players interact not only through the position of the other player, but through the distribution of actions, the controls, and I don't know how to do this kind of analysis in this case. Thank you.
So thank you very much for the talk. Are there any questions or remarks?
You need to use that. Oh, okay. So the conclusion with the independence of lowercase f on m is that if your running cost depends upon the behavior of the mass, then non-trivially, then there's no chance of efficiency.
There is no chance to, yeah, exactly.
Right.
Yeah.
Okay.
So in the simplest framework, you never have efficiency, basically, yeah. Which is, again,
which is
it's not extremely
reasonable.
surprising. Yeah.
Yes.
Yes, a few years back we studied the social problem with Peter and Mini, but we approached it with a person-to-person type of optimization. In other words, each player, you're trying to optimize social cost, but each player looks at its impact on the global cost individually, solves, so it has an associated personal cost, which depends on its index, and then we view it as a Nash equilibrium at that point. Each one has separate costs,
okay.
but, of course this is less general than attacking the. But I'm wondering, because the structure that you get is very close to a mean field game equation again if comparison in that case?
That's a nice
would be-
question. I've got no.
okay.
Yeah.
Okay. Thank you.
Further questions?
Yes, one last question. There's a lot of work on mean field type. Have you been looking?
Okay, so the necessary conditions are more or less related with mean field type control.
Okay,
That's mean field type control, indeed. Yeah.
Okay.
So the question was to compare mean field type control with mean field game, exactly. Yeah.